sir. Yeah. So Jim Hoorman's going to talk to us today about improving soil structure, reducing compaction, and reducing nutrient runoff.
Okay. Whew. Boy, am I wired up or what? All right. Has anybody not heard how I broke my leg? I'll give you the 2 seconds because I probably told this about 10 times. So I went to Punta Cana 2 weeks ago on vacation. Within 18 hours, I broke my leg. Went sailing, came back, and the wind was blowing, and I went to turn the sailboat around, and it started to tip over. Well, it has 2 tarps on it, and they're intercrossed. I have a small foot, went right in there, went to the right, I went to the left, broke it in 2 places. So that's how I did that. It was just a wonderful vacation, I must say that. So, yeah, so, all right. So we're going to talk a little bit. I'm actually going to follow up on some of the things that we talked about. We'll try to get to that quick, but we're going to first talk about soil structure and just a little bit, and then we're going to get into a little bit more on the phosphorus and what's going on with the phosphorus runoff. So again, just kind of background, but the most important part of this graph is yet, I think Frank alluded to this, 50% of it should be pore space, but the other part that's really important is you got to have a lot of organic matter. That organic matter is really important. It controls, it's like your brain and your heart controls so many functions in the soil. It controls your pH. It buffers your pH. It controls how many nutrients are stored. There's so many nutrients that are chelated and tied up. Has a tremendously high cation exchange capacity. So as you increase organic matter, you should have less runoff of all these essential nutrients. What has happened to our organic matter levels in our soils in the last 50 to 100 years? They're down 50% on average. Some places 70 to 80%. So again, we've got to learn how to build that organic matter back into that soil. This is just some information. This is actually some of Randall Reeder's information. I'm just going to highlight a few things. But compaction can reduce your yields by up to 60%. And the other thing is, it has been shown to persist for up to 9 years. More and more, we're understanding that we don't have so much a compaction problem as we do an infiltration problem. If we can get that water to move down through that soil profile and to interact, especially with that organic matter, I think we're going to solve a lot of our problems. So we'll talk about this as we go. I'm going to do this fairly quickly. Also, Randall found that 80% of our soil compaction comes from that first trip that you do over the soil. So guys that are doing tillage for 1 year, no till it the next, and then till it up the next year, unfortunately, you're not getting a whole lot of benefit from that. This goes directly back to what Ron Rogowski, I think. It came from him. I think he says you lose 80% of the benefits of your soil when you till it the first time, okay? So that's why you got to understand why it's so important that I'm really emphatic. Long-term no-till, long-term cover crops. It's not going to be quick, but that's the way that I think we need to go to solve some of these problems, okay? This just shows some of the bulk densities, and when we're looking at bulk density, all we're looking at is the weight in grams divided by the volume. And usually I show you my brick and my sponges. We don't have time to go over that, but the higher the number just means the more dense it is, and it means there's more, if you're looking at soil, more mineral portion. But as that number gets bigger, you have a lot less pore space. So ideally, if you've got about a 1.3, the maximum bulk density of a soil is about 2.6, 2.65. So if I have 1.3 divided by 2.65, I have 50% pore space. About 50% of that is solid. Okay? So that just gives you an idea. As you get up into these 1.7, 1.9, you've lost a tremendous amount of your pore space. 25, 30, 35% of your pore space is gone because of that, okay? I'm talking about how much of that 50% is left, okay? Just shows you some things where we start to get into problems. If you're looking at about 1.6, some of you guys like to use these penetrometers, and we're looking at, what is it, pounds per square inch. So about a 1.6 is going to be equal to about 250 pounds per square inch. 1.8 is about 300 pounds per square inch. At 1.6, the roots start to become limiting and they can't get down through that soil profile. At 1.8, they go off at a right-hand angle. And that's where we have our compacted layer. We can still find a compacted layer from that plow layer that we did 50, 60 years ago, okay? But we're now starting to see a new plow layer. And that's what we're going to talk about here in a little bit, coming from the vertical tillage, all right? We'll talk about that. Here's some subsoiling, some things we learned with Randall at our Hoytville site. Where we had conventional tillage and we subsoiled, we got a yield gain of 1 to 3 bushel or about 3%. Where we did the soybeans, the gain was about 2 to 5 bushel or 10%. What happened when we did it on the no-till? Got the exact opposite. It went down. Why is that? Because the soil is starting to heal itself. The other thing is, when you take a deep ripper like that, is that soil ever really dry all the way down? A lot of times you're smearing the sidewalls and you're causing all kinds of problems. The only way you're going to break that up is with live roots, okay? But it's a slower proposition. This is what a subsoiler can do. Immediate change in soil structure 18 inches deep. It'll increase your infiltration short term, but it's only going to go down to probably about whatever the level is that you're doing the subsoiling, but it's also going to leave that soil susceptible later to not only erosion, but also to more compaction, okay? Because you're not really helping it. Here's what cover crops do. It's a slower change. It may go 3 feet or deeper, okay? But it increases your infiltration, so it also helps protect that soil from erosion. And you're going to add nutrients, and you're also got that organic matter there to tie it up. That's what the cover crops do. It fits into a continuous no-till system, and again, it's going to help us protect against future compaction. One of the key things, I've said it so many times in my lifetime, what do live roots do? They absorb soluble nitrogen, soluble phosphorus, and a lot of these nutrients. So if you have a network of roots out there, and you've got this wetting front, and you spread it out, and you've got all these roots in there, you've got an opportunity to tie up those nutrients. And then what are we finding out? We have a lot of farmers now that are starting to check their tile lines, and they're noticing something. They'll look at their tile lines, and it takes longer for the water to get there, but then when it comes out, it's got a clearer color to it. It's not brown, okay? They'll go over and look at their neighbors, and it's coming off the soil surface, or it's shooting out the tile line, and it's dark. It means it has a lot of soil in it, okay? Now, if they actually test the concentrations, generally they'll find that they have a little bit less, but the problem with this is we don't have the volume. So it's really a two-part step. You need concentration times the volume of that water. You also need the concentration of the sediment times the volume of the sediment coming out to figure out how many pounds of phosphorus that we're losing, okay? So that's what's really important, that we understand some of these processes. These just show how we can resist that soil compaction, and obviously subsoiling is not very good. The more you aerate it, you're gonna dry it out. The deeper you moorboard plow it. Strip tilling's a little better. Shallow tillage, airway, Phoenix Harrow, you're not gonna do as much damage, but if you already have the damage below there, you're not fixing that damage until you get some roots in there, okay? So that's part of the problem. No-till, light residue, bare ground's not going to be what's even better is having more residue. It will cushion the weight of your tractor and your implements and your combine and your grain carts. And then if we can go to no-till with a growing cover crop, and then ideally would be this last one, continuous no-till, controlled traffic, and a cover crop. That's kind of the way we're ranking this, and that's the direction we would like to see you go. Move up to the top, not down to the bottom. This just shows some of the benefits of that long-term no-till. If you look in the right-hand corner, this was a study done by Stuart Dykert in Penn State. And what they did is, this was a field that had been conventionally tilled. Look at the ruts on that truck. Now, the truck had the same amount of weight on all 4 of these fields. If you look at the one on the left of that, I think it's no-till after about 1 year. You'll notice that the ruts aren't nearly as deep. And then you look up here, no-till after 2 years. And then no-till after 3, you can barely see the ruts, because here's the key thing they found out. The soil becomes firmer, but it becomes softer. Firmer, but softer. That's how they're describing it. It can hold the weight, it's firmer, but you can actually go in that soil and that soil will crumble on you. Okay, because why? Because it has good aggregate stability. All right, that's what we're trying to get at, aggregate stability. All right, that's what we're hoping. These are the best ones to fight compaction. Your grassy fibrous roots, most of those are going to live year round. The sorghum sudan, obviously, that's an annual. That has probably the most roots and does a really good job. But annual ryegrass, cereal rye, even oats, even though they'll die out, they're the ones that will really help us with compaction. The brassicas, we all know about the Daikon radish. You don't have to have the real big ones. I think, as Dave Brand has said, 1 inch to 1.5 inches wide and maybe 2 feet, 3 feet deep is a great, okay? It's a natural it does natural bioturbation with that. So that's a natural way of doing it. Turnips aren't quite as good because they're pretty shallow rooted. For legumes, really just about any of them work pretty good. The hairy vetch have a lot of roots. The cowpeas, sweet clover, red clover, and the winter peas, okay? Winter peas don't have quite as much. And then if you got surface compaction, those buckwheat doesn't go very deep. It only goes a couple inches, but it really helps with surface compaction, and also phacelia's in that same boat. If you really want to go deep, those sunflowers can go down there 4-5 feet deep. Okay, so it depends on where your compacted layers are. Let's talk a little bit about the surface runoff. And this is what I alluded to before. It's really dependent on 2 things, your soil P concentration along with the transport factor. And I always like to tell this story because this comes from Dr. Sharpley. They did a study in Pennsylvania, and they had this stream, and right next to the stream they had low phosphorus concentration. A little bit further away from the stream, they started to have a much higher phosphorus concentration, and it's starting to slope a little bit. And then a little bit further, way up on top, basically a little bit further away, they had the highest, very high soil phosphorus concentration. Where did most of the phosphorus come from after they had a major rainfall event? Most of it came actually right next to where the ditch was. The lowest phosphorus concentration is where they found they had the most, because it all has to do with transport. Now, what would be the absolute worst situation? High phosphorus concentration right next to a ditch. And that represents, we're finding out, these numbers vary, but probably 80% of our phosphorus may be coming from only about 20% of our soil. And some of these numbers, you're going to hear a lot of different numbers. Somebody will say, 60% is coming from 40%. But you get the idea. Not every acre is the same. Transport is very important. What is one way that we're increasing transport? All these inlets. The guys bring the tile lines to the surface, and I think Doug Smith did a really good job of talking about blind inlets and some of the things that we're doing there to filter out that phosphorus and keep that phosphorus on the land so that we don't have that direct transport to our ditches, okay? So just talking a little bit about that. This just shows how phosphorus is tied up organically. 50 to 75% of it is tied up organically, okay? So what you have is a clay particle. You have your phosphorus, this is your soluble reactive phosphorus, and then wrapped around that is your organic matter. Now, if I lose my organic matter, which is protecting that, has a very high cation exchange capacity, if I lose that, now I lose my protective shield, and if I drop this particulate phosphorus into water, how much of that becomes bioavailable? Just recently, Libby Dayton did a study, found out that 70% of that particulate phosphorus can become bioavailable. Bioavailable means it's your soluble reactive phosphorus. That's what your plants take up, and that's what your algae are taking up, okay? Your harmful algae blooms, all right? So the more carbon we can get into the soil, hopefully what we're doing is we're gonna put a long chain on it, and it's gonna attach to other soil particles and kind of clump up. It's less likely to leave the soil system, okay? That's what we're trying to do. We're putting this long carbon chain on there to keep it in the soil profile. Now, there's a number of different ways that phosphorus is tied up. This is some new research that we're doing. We did a little bit of this at Ohio State with Rafiq Islam and Alan Sendermeyer. We were looking at the different phosphorus speciations. So you can tie it up organically in the humus. That's tied up very long term. Or you can tie it up in an active form. So those are the root exudates and all that kind of liquid carbon that's out there, okay? That's what gives us really good soil structure. And those forms are probably a little more stable in the form that they're still plant available, but they got a long carbon chain on it. Hopefully they're gonna latch onto something and not leach out of the soil. Then we have these three other ways, basically, that phosphorus is tied up. It can be tied up with calcium and magnesium. It can be tied up with iron and aluminum, okay? So those are our inorganic forms. And that soluble reactive phosphorus that I'm talking about, that's also inorganic. Why is it inorganic? Because there's no carbon attached to it. So here's what we found out. We were doing some research, and of course I see this all the time in Northwest Ohio. Under saturated soil conditions, iron goes from the F3, which is make sure I get this right, the ferric to the ferrous state. So when I have saturated soil conditions, you can look in the soil, and what's happening is, if it's well aerated, you're gonna see this kind of pinkish color in the soil, okay? That means it's well aerated, it's got an extra phosphorus attached to it. When the soil becomes saturated, that ferric turns to ferrous and it releases soluble reactive phosphorus, okay? Now I have one question for you folks. Has anybody in their lifetime ever seen standing water in Northwest Ohio? Because of poor soil structure. So this is what's going on. Remember, we're losing 1.2 pounds of phosphorus on average per acre. What do they want us to get down to? 0.4, okay? So it's just a little bit of change there. We're seeing more, and what's causing this compaction? What about vertical tillage? We've now got a vertical tilt tool that goes down about 2 to 3 inches, and now our bucket, rather than being 6 to 7 inches deep, is only about 2 to 3 inches deep. So now if we get a rainfall event, guess what? It runs off or it saturates quickly, takes the water with it, either gets into the ditch or goes directly down through a preferential flow or a crack right into our ditch. Now that's only half the bad news, guys. What happens when that soil starts to dry out? That soil, that iron's looking for phosphorus, and it's gonna steal any soluble reactive phosphorus. It has enough strength that it can steal it from the calcium. So gypsum is a great thing to tie up the phosphorus, but if you have a high iron content in your soil and that iron is not fulfilled where it wants to be, it can steal it from that gypsum, okay? What are farmers saying? I'm putting on this phosphorus, it seems to disappear, and then all of a sudden I need more phosphorus in my soil. Could this be part of the explanation? I think it is a big part of what's going on, okay? So just wanted to show you that. This is some research that was done at Coshocton, and on the left-hand side, we're seeing a conventional tilled field. You can see that muddy water. Look at the no-till field. The water coming out of there is crystal clear. Matter of fact, they did 40 years of research, and on that conventional tilled field, they had over 1,500 inches of water runoff. How much water runoff did they get on the no-till site? 7 inches within the first 2 to 3 years, and then it stopped. Now, this picture was not taken from that site, but it kind of shows what I'm trying to explain to you, okay? So this picture is not what the picture that was done at the Coshocton site. Just want to make sure you understand that, all right? This just shows you the dynamic properties of the infiltration. Bare soils, we can get about 1/4 inch of water infiltration per hour. No-till actually goes down if you don't have any residue. What happens? You start to erode these soil particles and they start to bridge over and they're going to clog those pores. As you increase the residue, if we get up to 80% residue, now we can take in 1 acre-inch of water per hour, okay? Just shows you the importance of that residue in the soil, all right? This is a little research that we did, Rafiq and Alan Sundermeyer and myself. I think even Randall Reeder might have been involved with this. We decided to do some of this speciations on some fields. So we were looking at different rotations. Corn, soybeans, wheat, corn after corn, corn after soybeans, then corn. We looked at the alfalfa, grass, waterways, and forest. Come to find out, now we can't really tell too much from this slide. This is a snapshot. Either our glass is half full or it's half empty. Okay, so if you look at this, which one had the most soluble reactive phosphorus in the soil? Where we had live roots. Now my question to you is this. What happened to the soluble reactive phosphorus in the other fields? Did it just disappear? Was it already leached out? Or did it just not have as much? Can't tell from this slide, can't we? But we've got some other information. Maybe this will help explain it. So we look at the exchangeable phosphorus, and this is what we want to see. What had the lowest amount? Lowest amount was wherever we had soybeans. Makes sense. We don't have a lot of roots. Okay? So that's why we don't have as much exchangeable, that active carbon. And then if you look at, go over to the aluminum and the iron, which one had the highest amount of iron in the soil, took up the most? Again, where we had soybeans. That has the greatest potential for us for losing that phosphorus, okay? The more residue you have in there with your corn and the bigger your corn stalks are and all those roots, probably gonna have less of an issue with the phosphorus leaching out, okay? Now, we also did cover crops versus control. What did we find? The cover crops had 0.34, okay? What did the control? We just maybe hit it at the right time. Maybe it hadn't leached out yet. But all of a sudden, it is 1.42, or I'm sorry, 1.42, which is 4 times higher phosphorus in that soil profile. Is there anything there for it to attach to? Probably the iron, okay? That's the point I'm trying to make there. That's where we're looking at, okay? If we don't have organic matter, you don't have a live root, that's really the only place it can be tied up, calcium or the iron or the aluminum, okay? If you look at the exchangeable, it's the exact opposite. Those cover crops had anywhere from about 8.8 times more exchangeable phosphorus in there. That's the form that I'd like to see it in, either the exchangeable or in the humus. Same thing we did with stratification. The stratification with the cover crops was 0.46 compared to the control, which was 1.8. That's a difference of 4.5 times higher, okay? And again, where did we see the exchangeable? Right where we wanted to. The cover crops had the highest exchangeable, whereas the control had the least, okay? Almost a factor of 9. And then this is just another one that I did in Mercer County a couple years ago. We looked at a bunch of different fields, low, medium, high, extremely high. And then we also took a grass waterway, or not a grass waterway, it was right along kind of the road ditch. It had been in grass for over 75 years. We knew the history of that. And then we took a wooded area. And we looked at this on both Pewamow and Blount, and we got almost exactly the same results. What we would like to see is if you go to that lower right-hand corner right there, whoop, come on, there we go. I don't know if you can see that 9.5 down there, the higher the number, the better. Because we'd like this to be tied up in the residual versus being tied up in the aluminum. What happens once you start doing tillage? All these fields that were above there, the low, the medium, and the high, a lot of those had been either tilled or they were just starting on no-till, okay? So now you're looking at 5.3, and we're finding out that as you do tillage, guess what? You've lost a lot of your organic matter, so more and more of it is being tied up by that iron fraction in the soil, and pretty soon our numbers are dropping down to 1.7, 1.9. Look at what's going on here. We've got extremely high. We had soils that were 700 parts per million, okay? Now, I don't know if this specific field, I don't think was quite that high, but in some of those areas, the only thing it can tie up, if you don't have the organic matter there, is it's going to tie to the iron. That's a very unstable fraction, and when it rains, what happens? It's going to wash into our ditches, okay? So that was pretty quick. Just some other information. Now we're getting to the good stuff and the new things. I looked at a forested watershed. This came from Brady and Wiles, their book. They had soil organic P was 645 kilograms per hectare. Just take that times 0.9, and that tells you how many pounds per acre. They had inorganic P was about 275. Total runoff was about 0.3 or 0.24 pounds of phosphorus being lost per acre. Right next door to that, within 50 to 100 feet, they had this agricultural watershed. What was the soil organic P there? Well, it was about 314. Had 50% less soil organic matter. What was the inorganic fraction? Was somewhere around 976. So take that times 0.9. You're still well over probably 900 pounds of phosphorus per acre. Runoff was 2.41. That's about 2.1 pounds of phosphorus running off per acre. What did they find out? The mineralization was 4 times higher. The runoff was 8 times higher. Keeping that soil vegetated is going to improve the soil structure. It's also going to tie up your phosphorus, okay? So let's talk a little bit about phosphorus. How long do I have? 5 minutes. So here's what's going on. Large number, the thing that has changed the most is the weather. We have larger number, higher intensity, longer duration rain. We have a better environment for those cyanobacteria. The warmer it is, the worse it is. But here's some things that have changed. We've changed on the farm sites. We're now broadcasting our phosphorus. I don't know if you guys have studied this. This just came to my mind here just a little bit ago. We used to put on, what was the form of phosphorus we put on? O60O, okay? I believe that was right. Wasn't that triple phosphate? Had very... Oh, I'm sorry. Yes, that's right. I'm sorry. I'm trying to talk too fast. Anyways, that was very low solubility. Had a lot of other micronutrients. Then what did we go to? DAP and MAP. DAP and MAP have extremely high solubilities. That's part of the problem with what we're doing. And then as you go move down there, we now have our tiles closer together with more surface inlets. The fertilizer chemistry has changed a little bit. We've got tri-state recommendations that have this huge safety factor in it. We've got vertical tillage because now we got that compacted layer there. And also if you look down there a little bit further, we have Joe Nestor's theory. Goes right in with what I'm talking about. What has happened to the pH of the rainwater? It's become less acidic. The lower the acidity, as you increase your acidity, you get a lower number, 4.2 compared to 5.2. That's a factor of 1. As that moves up, that means that iron can hold on to that phosphorus less strong. It's not as strong of attachment. So as we've changed our rainwater, now the phosphorus can be lost a lot easier by the iron in the soil because we changed the pH of that soil. All right, I'm going to skip some things. I want to get to this because this is huge. This is Doug Smith, who is right here. He did vertical tillage and long-term no-till. 3 times higher soluble reactive phosphorus where we had the vertical tillage. Then we looked at total phosphorus. Vertical tillage versus no-till. 3 times higher total phosphorus being lost from those fields. Okay? Then we did, I believe it is, I can't read that myself. I don't remember. Can somebody read that? Is that sediment? So the sediment was 4 to 5 times higher. Okay? So if that sediment is highly enriched in phosphorus, what's going to happen? It's going to be lost with that vertical tillage. And he also showed this. So down in the lower hand corner is the no-till, whereas where we're doing the vertical tillage, we get it all over the board. Okay? It depends probably on how much soil organic matter is there. Last thing, 6 quick pictures. Field 1 and 2 are conventional. Field 3 is no-till with a cereal rye. Look at that muddy water. Look at how high that ditch is. This was done in Fort Wayne. Look at how that dirty water is. Okay, this is at field 2. There's a catch basin right there. But now, what's going on with field 3? The water level is lower in that ditch. There's less water coming off this field. And what else? That water is clear, and you can actually see that water entering that ditch. I don't know what tells a story better than those couple pictures, folks. Okay, so that's about what I have. If we have one question, I'll take it quick, and if we don't, we'll wrap it up. Thanks for your attention. Who's next? We have a break or
Okay,
where
we have a break now. No
All right.
questions? Okay, we're gonna go into break and we'll be back at 3-ish. 3:05, back in this room.